The purpose of this video is to help you understand how we can use the periodic law in order to predict some information about some of the properties of atoms. So the periodic law was originally put out by Mendeleev. When he created his first periodic table, he realized that the properties of atoms, things like reactivity, would repeat periodically or at regular intervals if you list them out in a certain order. Now we already know that Mendeleev was listing his elements based on atomic weight, but later we realized there were some elements that kind of switched places if we did that. And once we realized that the protons actually existed, once we had some better technology to figure out information about the nucleus, we realized that really what we want to list elements by is their atomic numbers, or the number of protons in their nucleus. So the periodic law just states if elements are listed by the atomic number, their properties will repeat at regular intervals. And those properties that repeat are actually quite numerous. We're going to focus on just this list here for this year, and we're really going to make this into a mini unit where we focus on the first several today. Then we're going to look at reactivity and even have some lab activities there. And then we'll focus on the other three later on next week. So throughout this little mini unit, your goal is to be able to look at each of these properties and do the four following things with each. You want to be able to define the property. So what is atomic radius? You want to be able to look on a periodic table and identify what is the trend of that property going down a group. Does it get bigger or smaller? And why? You need to be able to explain it. You need to be able to do the same thing across a period from left to right, making sure again you can explain it. And then if I give you a list of elements, you need to be able to tell me which is the largest and smallest atomic radius, or which is the highest or lowest electronegativity. For each of the properties, you should be able to identify highs and lows, or minimums and maximums, based on their location on the table. So in order to get started, we're going to first look at the atomic radius and the trends that are involved with the atomic radius. So based on your reading, you should have a general idea of what I mean by atomic radius. If we think about an atom as being a sphere, we know now that it's not exactly a sphere, and we know that that boundary is kind of inexact because the electrons are moving. But if we consider it a sphere, we can think about the distance from the very center of the nucleus to the very outer valence electron, and that would be our atomic radius. Now, of course, that's going to be incredibly difficult to measure, only because those electrons are in constant motion. So usually when we're talking about the atomic radius, it's actually measured by taking two atoms that are identical and next to each other and measuring the distance from one nucleus to the other nucleus, and then just simply dividing that in half. Either way, we get this distance that really measures from the nucleus to the outermost electron. So when we're looking at defining atomic radius, we're going to say the definition is the distance from the nucleus to the outermost valence electron. Now remember, after our definition, the next thing we want to do is think about what happens to atomic radius as you go down the group on the periodic table. So when we think about our periodic table and we think about how it's being built, we know based on our understanding from the last lessons that as you go down the periodic table, you get more and more energy levels. So elements in this first row had 1 energy level, 2 energy levels, 3 energy levels, and we continue that trend the whole way down until we get to the 7th energy level. As you add more and more energy levels, the size of the actual radius of the atom is going to, of course, increase. So when we're talking about identifying the trend down a group, all we would say is that the atomic radius increases down a group. And then when we try to explain it, we can just simply cite the fact that there's more energy levels. So atomic radius increases down a group because more energy levels are added. Across a period, it's going to be a little bit different, because as you go across a period, you're not adding energy levels. You're also not removing them. You're actually keeping the same number of energy levels the entire way across the period. So you might think that across the period, the size of the atom should remain constant. However, there is one thing that actually does affect the size of the atom across the period, and that's the actual electrical interactions. As you go across the period, you get more and more electrons in that valence shell. You also wind up with more and more protons pulling on those electrons. So since we have more positives and more negatives, as you go across the period, the size of the atom will actually shrink in just a little bit. And the reason that it does shrink in, the reason that it does get reduced, is because that electrostatic attraction. More positive, more negative, more force of attraction, a smaller radius. So one more time, our goal here is that you can tell me what happens down a group and across a period and why. So when we're looking at atomic radius, we can very easily say down a group, the atomic radius increases because there are more energy levels added. When you're going across a period, the atomic radius will decrease because there are more protons and electrons, so the force of attraction is greater. So increases down, decreases across, which then leaves us to the idea of determining the maximum and minimums. And when we're talking about atomic radius, we're usually just going to call that the largest atom and the smallest atom. So when you see large atom, small atom, don't think mass. Instead, think the radius, the actual size or the volume. And in order to think about that, we're going to look at an actual periodic table. So on our periodic table, we know that it increases going down and we know that it decreases going across. So what we can do is think, where are the minimum and maximum regions? Well, if it increases going down, the biggest is going to be on the bottom. And if it decreases going across, the smallest is going to be over on the right side. So if we go here, this is going to have the largest atomic radius. And up here would be the smallest atomic radius. Largest atomic radius, smallest atomic radius. As you go down, they get bigger. As you go across, they get smaller. And really, now that we know where the minimum and the maximum are, we can compare other elements. So for instance, if I asked you about scandium versus yttrium versus lanthanum, you would say lanthanum is the largest because it's closest to francium. It's furthest down and furthest to the left. Scandium would be the smallest. It's closest to helium. It's also higher up and closest to the right. If I'm looking at something like this, technetium, number 43 here, would be the largest. Cobalt would be the smallest. If I'm looking at something like this, still the largest is obvious because mercury, number 80 here, is definitely closest to francium, but smallest is a little bit trickier because we have one thing that's higher up, but one thing that's further over to the right. In a case like that, where you have one thing that is smaller in terms of up and down and the other thing that would be smaller left to right, always go with the smallest being the one with the least energy levels. Energy levels make more of a difference than the little bit of a squeeze that you would experience going across. So again, when we're looking at atomic radius, we know that the atomic radius is the distance from the nucleus to the outermost valence electron. We know that as you go down a group, it increases because you have more energy levels. And when you go across a period, it decreases because you have a greater force of attraction. We know that helium is the smallest on the table. We know francium is the largest. And we know that if we're comparing different elements, just in a quiz type of fashion, we can always look and say which one's closest to helium, that'll be the smallest, which one's closest to francium, that'll be the largest, and if there's any weird situations where you have one thing higher but one thing over to the right further, or honestly the opposite too, if you have one thing lower and one thing over to the left more, you're always going to look at up and down being more important than left to right for atomic radius. At this point, you're going to have some chance to just practice a few questions.